So, just a brief bit of history before we dive into model-based testing and how we've applied it. What happened is, a long time ago, we had this project to create all the technical documentation. And these are some of the stats that you see. One of the important things from my perspective was we were ramping up hundreds of engineers, mostly vendors, and they were mostly inexperienced. So we had to define a process and a methodology that would scale very quickly to a large number of people. And so that's kind of the crux of how and why we chose, a great extent, sometimes model-based testing. In Beijing, we had a tool center. You'll learn more about the tool we use. It's publicly available. And the result of all this years of effort was that we found a lot of document bugs, TDIs, and made a lot of corrections, which hopefully you've all seen and reflected in what you work with now. So basically, our goal was we had technical documents, and we were requested to create test suites that verify that technical document to show that an implementation matches what that document says. And so at very high level, what we do is we want to validate the consistency of the document, that it doesn't say at one point you set something to 1, and some other point it says something to 2, and then they contradict each other. We also, in a very weird kind of way, simulate an implementation process. So I'm going to talk mostly about how to test a server, but you can reverse that, and we also do, which is how to test a client. But if I want to test like SMB server, then I need a client, and that will be our test suite that's going to talk to the server. So there's aspects of the implementation that we have to do as part of implementing the test suite as well. So what we do is we scan the document for normative statements. Now, our documents have been talked about as being like RFCs on steroids. And if you read RFCs, they actually don't make the normative statements that clear sometimes. And so many of our documents are at least usually more clear with capital must, capital should, capital may, but they don't always state it like that. And so it still requires a careful eye to look for normative statements. What we do for all those statements is we translate them into assertions, things that must be true about any implementation that conforms to that document. And then one of the purposes of getting accuracy of our document is making sure that the document follows what Windows does. So we run those assertions against Windows, and when it fails, and this was quite a shock for me as a tester, it meant not that the product was wrong, because by definition the product is the protocol. It meant that the documentation was wrong, and we had to go fix the documentation. So we were checking against Windows to make sure that our documents accurately reflected the protocol as implemented. And we'll talk about this more later and a lot more in, I think, the second talk, the goal was to make these test suites not just for Windows, but to make them portable. So a little bit more about model-based testing. What we do is we start off with requirements, and I talked about extracting those from our technical documents. And then we have somebody author a model. And the model is a high-level abstraction. And that's the hardest part we had teaching people, is many vendors come straight out of school. They know computer science. They know how to code. They really don't know how to abstract. They really don't know how to design. And models are really about designing and abstraction and much less about coding. And just by building a model, you get lots of feedbacks on the requirements. This requirement is ambiguous. This requirement is contradictory. This requirement, we have no idea when it applies. So lots of feedback comes just from doing the model. Now, in our overall process, which is what I'm not covering today, and you can read papers about it, there's actually another step before this, which we call document reading, which is just by careful reading of the document, you can find lots of problems as well. So first stage is reading the document. Second stage is modeling it. From the model, and this is the power that we're going to talk about, we can generate test cases, which basically means inputs and verifying outputs. So what we call traditional testing, what most people do for testing is what we call design by hand or code by hand the test case. You say, okay, I need a test case that looks like this. Now I'm going to write code to implement that test case. I thought of another test case. I'm going to write code to implement a second test case. And I successfully brainwashed these vendors so that they consider that manual testing. Manual testing is when you write the tests by hand. Of course, we have automated execution, okay? And then you probably have automated execution. But how many of you write your tests by hand, one by one? Yes. We call that manual testing. Automated testing is when you generate the tests. We then run the tests against our implementation. We check to see what we get. This is all standard testing. And we get a verdict. Either we got the expected results or we didn't get the expected results. And in a normal product, that means to me the implementation was buggy. But in our product, it almost always meant either we modeled it wrong, which is always a possibility. It's another piece of software. It's got bugs. Or the requirements were inaccurate. The technical document didn't actually reflect what the implementation did. So the folks that were implementing this, the vendors, they're not protocol experts. They're software designers, usually fresh out of school, not always. Some of them have industry experience. We like people who know something about protocols, but they may not know anything about a specific protocol. Clean room approach. So these documents are being implemented by folks like you who are not part of Microsoft and therefore don't have contact necessarily directly with the Microsoft developers. All of the folks who wrote the test suites had zero contact with the developers of the implementation. We considered that a key aspect. That's the clean room part, which is it was completely based on what they could derive from the document, not from talking to the implementers. Our documents, as you know, have a huge appendix frequently where we give the Windows-specific behaviors. You should do this. Windows does that. Okay? So what that means is we write the tests according to the spec, and then we have flags to say, oh, if you're Windows, we know certain more interpretations because we have the appendix of Windows behavior. Similarly, you should want to be able to configure these test suites to reflect your behavior for things like shoulds and mays. And again, what we're focusing on is document testing. We weren't testing how does SMB, the product, works. There's already a team within Microsoft that does that. We were, via clean room, verifying the document accurately reflects the protocol. So we take the technical document. We actually create something called a requirement spec, which originally was a spreadsheet. Now it's a fancy database. But similarly, and so we would go item by item so we can cross-reference into the document and say, this is a requirement, this is where it came from in the document, and we can trace it all the way through. We encode those same requirements, literally, the exact string, into the model. The model generates test suites, and it plugs that same string into the test suite. When we run the test suite, it logs information saying, I've showed at least once that this requirement was satisfied. And so we can extract all those and say, okay, from our logs, how many of the requirements that we were trying to cover actually got covered? Because it depends on configurations or scenarios, things like that. There could have even been intermittent errors. And finally, as netmon and network captures, we can also, when we're sending information over the wire, we actually have a pseudo protocol, TSAP, which is the Test Session Announce Protocol, I think. And it's like a one-line. It's basically putting comments into netmon is really what it's like, into netmon logs to say, hey, we're checking out this requirement, or we're running this test. And so we can even in the netmon capture say, here's a block of information between here and here that shows you data going across the wire that we're using to verify a requirement. The other thing that made this project, I think, very successful is we had very junior people in general as vendors, but we usually had very senior people as reviewers to monitor the work. And again, I'm not going into all the details of that, but we had a 4-phase approach where they would review the requirement spec that was produced, they would review the model that was produced, they reviewed the test suite that was produced, and finally they would review the output. that was produced. So 4 phases, each one is reviewed by independent senior people to verify that, for instance, you can get away with this in the code, and it requires reading the code to see, oh, I assert that this requirement was validated, but I didn't check anything. So why did you assert it? Well, it felt like it was done. You have to actually put a check in the code. We had to teach several vendors that. You got to put a check in the code before you can say you've validated a requirement. And all of this, especially the requirement spec, is the input for the model design. The other thing we learned, and this is kind of big for us, Microsoft, is when we took out this manual test coding, notice there's no test coding over here, we spent more time up front doing what's called modeling. So if you look, we would get started later, and I'm going to talk about what adapters mean in a couple slides. But overall, across the entire project, 250 projects, some of which we did traditionally, which means by hand generating the test cases, and some of which we did by modeling in terms of generating the test cases automatically, we saved 40%. And we've had Microsoft Research go over this for the statisticians there, and they've shown that statistically significant. So we actually have a project with enough size and material, et cetera. Law of average numbers helps us to show that this was actually valid. So why did Microsoft choose this way of doing tests rather than coding them by hand? We're looking to save money. You know? We want to do it the most efficient way. So in traditional test design, you take a feature, you come up with requirements, you manually generate the test cases, and frequently, and we even saw this in the very first test suite that was developed, you see people who validate one requirement at a time. And you get a lot of redundant code. Suppose you call a data structure, and it gets a data structure back, and there's like 10 items in the data structure. Well, they'd write 10 test cases. Send it, check field 1 in the data structure, test passed. Test 2, do the same thing, only check field 2 in the data structure. Test 3, say the same thing, but check the 3rd field in the data structure. Yeah, that's how you get lots and lots of code and not much testing. Also, and this came back from the fact that we had oversight from some other groups like the technical committee at the time, or even the European Union had somebody, and they were saying, well, how do you choose your test cases? Like, you have different people. Would they choose the same test cases? No. In fact, if you look at how test design, manual test design is done across the industry, you will rarely find 2 testers that will come up with the same test suite. This didn't feel good to the regulators who were monitoring what we did because it wasn't reproducible. So the idea of having to have humans to figure out what the test cases were didn't seem as good as having a model that automates the test case production, and all these test cases go against a single library, which is a common implementation. So the library doesn't have test cases, it just has the common code that the test cases need to execute. So the models I mentioned is done high-level abstraction. The test cases execute to that abstraction, and then we have a single implementation that translates that abstraction into on the wire. The other thing about test cases, and we have this a lot, is we started back before Windows 7, and then Windows 7 came, actually let me rephrase that. We started before Vista. We were doing protocols that were based in Vista, and then the document got updated for Vista, and then it got updated for Windows 7. So we knew that these are not one-shot test suites. You want them to be up to date with the latest shipping version, including SP1 or whatever. So updating or maintaining the test suite is just as important as generating it in the first place. And again, the way you do this manually is some requirement changes. So first of all, you have to scan for what the requirements changes are. That's true when we're doing modeling as well. And we actually have built a little tooling to help make that a little easier, but it's not that fancy. But then we have to figure out which test cases. We have to scan the test cases, say which test cases are affected by this requirement, and then go recode them. That's the way you do it by hand. With modeling, instead, we change the requirement. We have to go change the model code. So there's still work. But now, again, we push a button, generate the test cases, and sometimes we have to change the implementation to if it's a new feature that's being mapped in. But basically, it's a lot easier. The maintenance is more complete. We don't have to worry about scanning all the test cases. Whatever changes that impacts, the model understands and automatically handles. And my basic rule of thumb in maintaining test suites is ideally, if the product team was able to make a one-line change, then you should only have to make a one-line change in the test suite. With modeling, that becomes feasible. And I've seen it multiple times. Dev makes a one-line change. You make a one-line change in the model, and you can continue. As opposed to, I'll give the worst case if you've ever seen this. You've seen people have UI tests. And they go, oh, we're going to change the banner on our window. Oh, my UI tests are broken. I have to regenerate everything. What could be worse? So maintenance of test suites is actually a major cost, and another reason we use modeling. So I already mentioned all of this. We have the uniform sampling from one of our test sites. We have the productivity gain. Junior engineers, mostly fresh out of college, freshly trained. So this is not hard to learn. That's kind of the key part. There is a learning curve. Don't get me wrong. This is not something you pick up in an hour. But it's also not something that takes years of experience. So as I mentioned, the real problem is we work from an abstraction. And so our tests are represented at this abstract layer. And we have to get the data on the wire and back because we're talking about protocols on the wire. So TTCN3 has an example of that. We actually copied what they did, which is we're using what's called adapters. The term adapter actually comes from TTCN3. It's what they used for talking about switching from the abstraction to on the wire. And to make that easier, we have a protocol test framework so that our test adapters are written in a managed language. And they do automatic serialization and deserialization. And this is kind of key. So again, through tooling, we try to do as much in an automated fashion rather than hand coding. Hand coding is always expensive. The protocol-specific logging, the beacon packets are what I also called using the TSAP protocol, and it's how we get stuff into Netmon as we have these packets. The other thing that modeling does, and this is not unique to modeling, I actually recommend this to folks who are doing manual test case generation, is to think about keeping an abstract layer and breaking your test team up into two parts. One team worries about test cases. They should be, to some extent, testing experts, ideally. And the other team worries about translating an abstraction layer into stuff on the wire. This is not testing. This is straight software development. So you can pick up any software developer, say, here's the definition of my abstract interface, go implement it. And so that's what we do. We have a contract between the test case team and the adapter team, and this is the key part for you as third parties, pluggable. Different server setups, different transports. So by having this abstraction layer, we can say, oh, sometimes you're going over HTTP and sometimes you're going over TCP. But from the abstraction layer, it's just a blob that goes over each of those protocols. So the abstraction layer, it's the same test cases, but we specify a different adapter to put it on HTTP versus putting it on TCP. Also, as I said, different server setup. So we might have a different small class, a class of custom config, which you might have to completely throw out because it's based on Windows and using Windows code for automation. And you can implement your own. And usually we give you a way to do it completely manual, which means you can get started. But if you're going to run the tests over and over again, you'll quickly decide that you want to write a shell script or maybe some code to automate some of that. And then you can automatically get your server set up, because we don't know anything about specific implementations other than we have as an example, a Windows implementation. So this is how we actually split it up. We read the document, we understood the protocol, and then we split into two teams. First, we defined the actions. What are the messages, effectively, the actions of the protocol? Every message you send to a server is generally a request of some kind. It's an action. It may be a read-only action, give me data. And from these actions, that basically defined the interface that the adapter folks could go off and implement while the modeling folks were still creating the model. So we didn't wait for the model to be complete. All we had to do was get an agreement on that interface. The other thing you can do with the model is you can do what's called exploring. And I'll talk about this more in a couple slides. But exploring is a way to get a feel for whether or not what you've built, the model, really reflects what you expected. So you can run little scenarios through it and say, I believe the protocol allows these 10 messages in this order. If I try and do that with my model, would it do it? And if it says no, well, then I have a problem. One of two things is true. My model's wrong, or my misunderstanding the protocol that it allows those 10 steps. And most of the time, it's our model's wrong. So I will say that models are not easy to get right. They're software. But it's actually much more explicit than I see in many test cases. So many manual test cases are done as follows. Karnak the Magnificent. I know what the model is. The output for this must be 37. And that's what you'll find in the test case code. Do this, get 37. And now you know. And it's obvious, right? Where the 37 came from. Out of their head, because they computed in their head the model. Come on, how many people write tests like that? Almost everybody writes manual tests by having a model in their head of what to expect. And so we're just making it explicit. That's the ideal. We make it much more explicit what the model is. So the tool we use is Spec Explorer. It allows different styles, multiple languages, but we do all of ours in C#. But basically, you can use any .NET language. You could use Visual Basic if you prefer. This was key, asynchronous and non-deterministic. How many of you have heard of finite state machines? Basically everybody. This is not finite state machines. Finite state machines have real problems with asynchronous, non-deterministic systems. Writing finite state machines for those is very difficult. But this is what many of our protocols are. And even if the protocol is deterministic, let me rephrase that. Even if the system is deterministic, we will frequently treat parts of the system as non-deterministic. So if we have a very high-level protocol that's on top of about 3 or 4 other protocols, so we're on top of an HTTP protocol, which is on top of a TCP protocol, which is on top of an IP protocol, and if we knew all the details of all that stack, then we would know exactly what happens. But we're going, wow, that would be a lot of code to write all those things and keep track of them. So we just say, oh, any of these things could happen. Non-deterministically, it could be one of these 5 results. Because we're too lazy, abstraction-wise, to write all the code to figure out which particular one it is, because it doesn't matter to the protocol we are testing. It's just an artifact of the fact that we have protocols underneath us. Now, we can extract state machines from the model program, and letting computers do this is key because humans are really bad at doing it. And from that state machine, we generate code. We can also do model composition, though again, it's a tricky thing to do. So first of all, model composition assumes that you have some pieces of state that are shared or some actions that are shared. Otherwise, they're just 2 separate models and they don't interact. So you have to think up front if you want to do model composition and plan for it. And I'm not going to talk about that because that's actually one of the most advanced techniques. Spec Explorer is not just used for protocols. It's currently being used for testing the UI of Windows 7 Phone. It's being used for testing parts of SQL. So it's used throughout Microsoft internally. We also have an early adopter program. So there are folks in the automotive industry testing brakes and steering systems, et cetera, using this tool. So it's a generic tool, and we're talking about the specifics of using it for protocols. It's publicly available. You all have access to it. It's now oh, this is an old slide. My fault. Oh, I should switch slides here. So this is, let me go. So it's currently what's called a power tool for Visual Studio. It switched in last October. And in fact, this is not the right place to find it. Let me go switch my slides. Oh, you have it in the next one? Good. So it is now shipped. It's been out there for almost 2 years now. It's a power tool for Visual Studio. You can freely download if you have Visual Studio. So we developed this for over 250 protocols. Oh, this is definitely not the slide deck I wanted then. I merged 2 different slide decks too quickly. Let me just switch to the other slide deck because I think there's more information you guys would like to see with a little bit more detail about SMB. I put it? No. OK. My apologies. Last minute change didn't get in. So yes, I'm going to have to just wing it. But I'll make sure it's on the SharePoint for you later. Basically, what it's going to do is walk through a couple examples of, or describe from the SMB spec, what we actually do. So one of the things that you'll notice in our template for all of our technical documents is there's a section called 3.1. Anybody know what the title of 3.1 is? What? What? It's called the abstract data model. And you'll find such a section in all of our specs. So in the abstract data model, it says you can implement any way you want, but you have to be externally, that means on the wire, consistent with the model that we're describing in this abstract data model. So if you were writing a test suite at an abstract layer, what do you think you would model? It's really easy. We build the abstract data model as the state model of what we want to do. And then if you look at the actions, all the messages that come in, then it will have and state, oh, based on data that comes in on the message, I will change various parts of my abstract data model or check various parts of my abstract data model, and then I will build a message and send it back. So for instance, current uses and max uses are in SMB2. And so what it'll say is, when you first get to the share, the current uses is 0. Under certain conditions, when current uses is less than max uses, you'll get another usage. So you'll increase the current usages. And by the way, if you get a message when current uses equals max uses, then you must return this error. All of that's in the SMB2 spec. And all you do is you turn that around into code and requirements, and that's how you build a model. So you do just what the spec says. You declare a data type that says, oh, max uses, current uses. And the method that it does the initialization sets the current uses to 0. And the method that has to go check that is it equal to max uses and return an error, well, you just write that code, right? Current uses equal max uses, return error. And you'll get to this. I think you're going to be showing code, yes? But tomorrow you'll see actual code. You'll see that we just put in basically the little string from the spec. On, when current uses equals max uses, then you return this error. And as I already said, we'll log all that information in. So that's pretty much what I was going to cover. Questions? Clear as mud. So what you'll find, let me just say one last thing then about the training. So if you go up to the Spec Explorer site, you'll find out that we have a series of videos you can watch. It takes about 6 hours to watch them all. I wouldn't watch them all at once in one day. And that's effectively the same training we gave to our vendors. In fact, it was a training class that we ran internally that we were able to put up there. That introduces you to Spec Explorer, the tool, and gives you a very, very brief overview of model-based testing, the concept. In addition to that, we would usually spend about 2 days with vendors teaching them a little bit about how exactly we extract information from the document into a requirement spec and then into a model. The hard part, as I mentioned earlier, that I still don't know how to teach sufficiently well, is how to do good abstraction and design. Part of what we did, which is an industry sort of trend, is we wrote patterns. So we have a small pattern library for modeling based on what we observed that people were having trouble with, and we had a common solution to a set of problems. So we have a few patterns for modeling. The basic advantage that most of you will have, so to speak, is if you want to do modeling, is you have examples. We have hundreds of examples of real protocols modeled. And Spec Explorer, the tool, comes with about 10 examples, one of which is a pseudo SMB test suite. So it gives it's a small abstraction to illustrate rather than test SMB. So it's illustrating what a model looks like without all the details, because SMB, as you know, is a very complex protocol that you actually have to use for the real test suite. So you could study the simple one that comes as a sample of Spec Explorer, and when you think you understand it, then you could look at the real one and get really lost for a few days, because there's a lot of detail there. So if you're going to be using our test suites, and if you want to extend them and use them yourself, I highly recommend learning a little bit more about Spec Explorer. And in particular, Spec Explorer has this thing called CORD, C-O-R-D. And it's a own little custom language, which isn't too hard. You'll see many of examples of it. That lets you write scenarios. So the way we generally generate tests is we write a generic scenario, not a very detailed one. You can write it where you don't specify most of the parameters for most of the methods, because the legal values frequently can be derived by the model. So you write a very generic scenario, and then you give it to Spec Explorer. You say, here's my scenario written in CORD. Here's the model. Go generate tests that show that that scenario works. And it'll generate a whole series of tests. That's also a way you can restrict. Suppose you don't implement the full spec. You only implement a subset. So you might want to take the model and compose it with something that says, do everything except these things that I don't do. Maybe I don't do pipes. So kind of disregard all the pipe commands. And you could do that using Spec Explorer. Now, obviously, the test suites we run and generate do the full gamut, because that's what we need to do. But you could subset if you wanted to. OK, thank you.